Very good evening to everyone. First of all, I would like to thank the EMTP user group and the organizers for this platform to exchange our ideas. And I also thank my organizations, my head, Mr. Nathan sir, and my colleagues who have been supporting me in all aspects in this project. And in this presentation, we'll be looking into the insulation coordination study of transmission line. That we'll be focusing on the line performance improvement against lightning trip out. So in transmission lines, the inadvertent tripping of lines is mainly caused due to lightning strikes. So lightning strike is a basic problem which is causing unwanted trip outs. And there are various methods of mitigating this trip outs or reducing this trip out to acceptable levels. And among the various levels, installation of line surge arrestor is an effective way of improving this lighting performance. And it is of great interest for many electrical utilities and even for researchers because it is almost compatible for any systems. Because when we compare other mitigation techniques such as addition of additional ground wires or increasing the length of the insulator, we have lots of limitations and we need some design changes in the tower, which are all things difficult to implement these mitigations. And in addition to this, the LSA's nonlinear characteristics has a superior advantage and makes an ideal choice for as a mitigation technique in many scenarios. So in this study, we will be going through a procedure or a way to minimize the number of arresters that we want to install to have a best suitable strategy to meet a target flashover rate. That is what the utility wants to maintain. The preliminary analysis is being carried out using IEEE Flash program, which is an open source software that we will further briefly explain in the forthcoming slides. Further detailed installation coordination verification is done using EMTP software. So this is a very interesting part that we will discuss. Okay, let's move on to the methodology. The flashover rate of the line will be estimated using IEEE Flash program. The methodology consists of 3 steps. Step 1 is to assess the performance of the line. That is, what is the present scenario of the line? This is done using IEEE Flash program, which gives an estimate of the line flashover rate. So what is line flashover rate? Line flashover rate is nothing but a benchmark value of the line performance. It is the number of flashover per kilometer per year. It has been dictated in the standard IEEE 1243, and it's being implemented using IEEE Flash program. So using the IEEE Flash program, we'll be able to find the flashover rate of the line. And step 2 will be deciding the target flashover rate, which the utility wants to maintain. And it depends on various factors. It depends on the economic as a prime element. So we have to decide a target flashover rate which we want to maintain, depending on various factors. And the economics will be the prime concern. That is how many arresters we can economically install to achieve the target. And once we have decided the target flashover rate, next will be analyzing the various mitigation methods we can go on or implement to achieve this target. And the third and final step is installation coordination verification. Once we have selected our strategy to improve the lighting performance, we need to verify whether the selected strategy is in line with the installation coordination requirements. Okay, this slide briefly explains the step 1 and 2. So the process starts with data collection. We collect data like isochronic level, tower geometry, span, grounding, details, arrestor, arcing horn, all these things. And we evaluate the line performance using the flash program, and we compare with the target outage rate which we want to maintain. And suppose if it is meeting, then we can move on to the next step of installation verification. And if it is not meeting, then we will again look for mitigation measures like installation of surge arresters at critical towers or improving tower footing resistance at critical towers. So this process will be iterative and until we reach the target outage rate. And third and final step will be the installation coordination verification. Again, we will do extensive modeling of the network. So we will be modeling the critical tower locations that we have obtained from the previous analysis. And then the modeling will be based on the inputs that we will discuss what we consider in the next slides. After modeling, we'll estimate the flashover pattern and check the IC compliance. And if it is compliance is met, then we'll go on to the next step. If not, again, we will make additional mitigation measures that we will discuss in forthcoming slides. Then if the compliance is met, next we go on to the checking the arrestor rating, whether the selected arrestor can withstand the worst case condition that is probable. And finally, when we select the arrestor, we summarize the results and then we give the conclusion of recommendations where we need to install arrestor and what rating we need to install. So this is the basic data that we require. We require the isochronic level. We require the conductor dimensions, insulator dimensions, and the phase sequence in which the tower is configured, and the tower dimensions, and tower schedules, and tower footing resistance of each tower. These are all some critical data which is very important for this analysis. So next step is the line performance estimation. So we'll be estimating the present performance benchmark of the line under study. It will be done using an IEEE Flash program, as said earlier. This is a small history of IEEE Flash program. It was developed in late 1980s. And further updated version was also released in Flash 1.9. But it will not consider surge arresters as a mitigation. And at a parallel, EPRI had its own in-house tool called Lighting Protection Design Workstation. Later in 2000s, they released their in-house as an open source. So later in 2002, a new version of Flash was released, which is a combination of both this OpenETRAN and Flash. So now using this Flash 2.0, we can estimate the line performance both with and without arresters. So this is the result that we obtained from the IEEE Flash program. This gives the shielding failure rates, back flashover rate, and the total flashover rate of individual towers. This is a typical example of a 220 kV line spanning around 55 kilometers, and it has around totally 135 towers. And around in 135 towers is around 110 towers are suspension type, and the other remaining are angle types, C and D types. So exact tower dimensions were used for the analysis. So the tower footing resistance or also the measured actual site values were used for each individual towers. And flashover rates, if we look at this result, we find that around 8.1% of towers is having a very low flashover rate of 0.1 to 0.5, and around 30% is in the range of 0.5 to 1, and 60% of tower is in the range of 1 to 1.5, and around 4.4% is having a flashover rate more than 0.5. So from this analysis, we are able to filter out the towers which is vulnerable. So we see that around 4% towers, that is around 4 towers, is having very high flashover rate, causing major issue in the transmission network. So once the individual performance of the lines are estimated, the total line performance can be estimated using this analytical equation as dictated by the IEEE 1243. This is just calculated as a weighted sum of the span length. And accordingly, we have 1.02 as a total flashover rate of the entire line of 55-kilometer length. Black flashover rate is 0.41 and shielding failure is 0.6. So if we see that beyond 1.5, we have these vulnerable towers. We have listed out some vulnerable towers, and so next step will be the recommendations. So what is the best way to have improved line performance? So analyzing various techniques, the first step of mitigation measure will be improvement of tow footing resistance, where tow footing resistance is high. So in that aspect, we will be analyzing. So improving lighting performance of the line is greatest concern. Many practices for lighting performance improvement have been published and tested. So selecting the best one is what is important. So improvement of tow footing resistance and lighting surge arresters are the two effective options. So when we improve the tow footing resistance, again we estimate the flashover rate, and it is being observed here. And the case 2 is again with the improved tow footing resistance. Again we analyze the various strategies. So we have strategy 1, 2, and 3. Strategy 1, we install arresters only on the top cross arms, and we estimate the flashover rate once again. And strategy 2, what we do is we install arresters on middle cross arms, and again we estimate the flashover rates. And again the strategy 3, we install arresters on the bottom cross arms. So the flashover rate obtained for each strategy is being tabulated here, and we found we have a very good results for the tower number APE3. The strategy 2 works out to be very efficient, and for all other towers, strategy 3, that is arresters on bottom cross arms. So in this way, we analyze various strategies and we come with recommendations for best strategy. So after installation of arrestor, this is the improvement we observe. So actual flashover rate from 0.41 reduced to 0.4 with the improvement in TFR, then it has further reduced to 0.39. So the total flashover rate is reduced to 0.99, so less than 1. So once we have selected the strategy that we're going to employ for targeted line performance, the next exercise is the insulation coordination verifications. Because once if we change any topology or we include or exclude any device into the network, the reflection and refraction nature of reflection is going to change, and you need to verify that the insulation coordination is still intact. So there is a possibility of fault being transferred to the adjacent towers. So that's what is being explained here. So having decided the 4 identified towers as per strategy, it is necessary to evaluate the performance of the adjacent towers without LSA. So suppose we are selecting this center tower as a tower, as a vulnerable tower, and if we are going for an LSA installation, we need to analyze the performance of the adjacent towers in relation to LSA installation, because we have now installed LSA in this adjacent tower. So the performance of the adjacent tower without LSA depends on the magnitude of overvoltage developed, which further in turn depend on the footing impedance of the stricken tower. So a simulation of back flashover is being carried out for the representative section, that is the vulnerable sections that will be selected, and we check whether there is trip out of adjacent tower after installation of LJ. So let's go on to the modeling. So modeling, lightning stroke is being modeled as a concave CG wave shape. And transmission line, we use multi-phase untransport distributor parameter, which is also frequency dependent model. Tower is being modeled as a lossless uniform transmission line model. Insulator is modeled as a voltaic curve model. We do have multiple models, but we have fine-tuned the modeling with various models available in the literature, and we have matched with the IEEE flash critical current values, and we have finalized the modeling. So we have validated with the flash and line termination with the matching impedance to avoid reflections at the end, unnecessary reflections. And our footing resistance, we use a 50 Hz value instead of impulse value because it gives a conservative result. So this is the modeling of the network. The first, the tower where we take the lightning is being modeled as detailed with all cross arms and impedance detailed tower model as per the SIGRI technical brochure 839. So each span is modeled as a frequency dependent span, and this is it is given as line model. And the last we have EZP, it is the line termination matching impedance, and matching impedance will be equal to the impedance of the previous span, so that in order to avoid the reflections. So this is the EMTP model. So now what we do is we compare the tripping pattern before and after installation of lightning arresters. So we compare whether the performance of the adjacent tower is degraded or improved before and after installation. So if we take a case of this tower 22, we do the lightning strike on tower 22, which is identified as a vulnerable tower, and we observe whether at what critical current is getting flashover. So without arrestor, we observe it is flashing over at 80 kiloamps, and the adjacent towers are flashing over at 130 kiloamps. Whereas after installation of surge arresters at tower 22 and no surge arresters on other towers, we observe that the lightning flashover critical current has increased to 135 kiloamps. So we see the improvement in the line performance after installation of arresters. In this way, we verify the spots where we install arresters. So this is a process done for each spans where we install arresters or representative section in case we have a large number of arrestor installation. So this is the chilling failure waveform before and after installation of arresters. This is without LSA and this is with LSA. So we can observe that the flashover is not observed after installation of arrestor. And similarly, the black flashover waveforms. So from the analysis, what we infer is that from all the tables, we observe that the critical current to flashover of adjacent tower has increased with the installation of LSA on the second tower, and therefore there is no case of fault transfer to adjacent towers. The absence of fault transfer is due to the good footing resistance maintained. So since we are able to maintain a very good tower footing resistance of 15 ohms and below, this phenomenon of fault transfer to adjacent tower was not identified, or it's not probable. So this is a crucial parameter. So TFR value has to be maintained well below this limit in order to avoid degradation of performance even after the installation of surge arresters. So once we verify the installation coordination requirements, that is improved performance, next thing will we have to select the proper lightning arresters. So we need to select the energy requirement of the lightning arrestor being installed. So the SIGRI 55 brochure recommends this. So according to SIGRI, we take the Burgess data, which gives the maximum charge that is being measured in a lightning stroke, and it is 40 coulombs for negative flash and 350 coulombs for positive flash. And since the negative flash is what or 90% of lightnings are of negative flash, and positive flash are very less probable, this 40 coulombs can be regarded as practical maximum. So in EMTP, we do simulate the same network again with the same model. We carry out this we strike a single lightning strike with 40 coulomb of current to the tower. And we vary the tower footing resistance from 10 ohms, 50 ohms, and 100 ohms. We verify in all these conditions. The 10 ohms represent a very good condition of footing resistance. 50 ohms is poor condition, and 100 ohms represent unacceptably high and high tower footing resistance conditions. So in all these conditions, we verify whether if we inject a maximum probable charge value of 40 coulomb, the arrestor is able to withstand or not. So this is the tabulation. So values of tower footing resistance, we inject the current. So we inject the maximum shielding failure current for the tower. In this tower, it is 20 kA. So to carry a 40 coulomb, we have a daily time of 800 microseconds. Similarly, back flashover, we inject the maximum probable current of 200 kA. So to get 40 coulomb, we have adjust the tail time to 300 microseconds. In this way, we inject 40 coulomb of charge into the arrestor, and we observe the discharge current and energy, and we take the maximum of this and select the energy requirement based on the maximum. So this has to be done for each strategy, because the energy sharing between the arrestors varies with the strategy. So suppose we in the whole line, if you are using only two strategies, then we can just take a representative section and analyze these two strategies alone. So what we observed is the maximum energy was 1194.28 kilojoules, and if we have a rated voltage of 198 kV, the energy handling requirement is 6.03 kilojoules per kV. Therefore, 198 kV arrestors with the energy capability of 7 kilojoules per kV is recommended. So these are the energy waveforms for various values of tower footing resistances. So next part is correlations. So the correlation between the fault event of the lightning activity and lightning activity is essential for effective placement of LSA. Since lightning is being a natural phenomena and it's of random event, fault events that could occur at location not identified by simulation studies. So there could be still faults even after our analysis in locations where we haven't identified. So in order to fill this gap, we need a real-time monitoring and correlation. So we need several recorded data to correlate with the events occurred in the nearby lightning activity to match the events and select the vulnerable jobs. And this can be done using these methods. We can use the SCADA data. We need the timestamp from the SCADA data and type of event, or from where it is, whether it is overhead line or where. Next, lightning location data. From this, if we have a lightning location system, we can extract the timestamp of lightning activity, amplitude of lightning current, and also we can get the probability. So once we have all these, over a period of time, we can use the distribution of local distribution rather than the default IEEE or SIGRI current distribution. Similarly, in relay also, we can extract the timestamp, distance of the event from the substation and which phase is affected. Similarly, arrestor has monitoring systems. You can again collect the timestamp, surge current amplitude, and location. So once we have all these data, we can correlate with them and identify the critical towers and have mitigation on those towers, selected towers. So after LSA installation, we should continue to monitor the performance, assess and evaluate if the goal of the project is achieved, and we can identify the deficiency in data collection to improve the future evaluation. So basically, we want to identify the exact locations of this frequent lightning activity, which is easier when we have all these data. So the conclusion is we can significantly improve the reliability by strategic placement of arresters. And after placement of arresters, we need a continuous monitoring of these events and correlation over a long period of time, so that we can further optimize this placement of arresters and reduce the lightning flashover rate still further to the best possible level. Thank you.